sometimes we'll encounter integrals that are difficult to evaluate. Fortunately, someone has gone out, actually many people have gone out, and actually solved some of these integrals for us, and so we can look them up in a table of integrals. Let's take, for example, these two integrals that are listed here at the top of the page. I notice both involve the natural logarithm. If I look at the first one individually, I notice that I have an x to the fifth plus 1 in two places. The derivative of x to the fifth plus 1 is 5x to the fourth, and so it seems like a substitution might be in order here. In particular, u equals x to the fifth plus 1. In that case, du is 5x to the fourth dx. The second one, again, has that natural logarithm. If you let u be equal to the tangent of x, because there are two occurrences of it, and because the derivative of the tangent is there in the numerator, we end up with u equals tangent x, du equals secant squared of x, dx. And when we make the substitution, each of them we get du over u times the natural log of u. Now this actually can be done with an ordinary substitution, a second substitution that is, but we could also look it up, the formula for this in a table of integrals, and we see from a table of integrals, which I'll describe here in a moment, that this is the formula for such an integral. And so in each case, we can go ahead and use this formula and replace the u by the u's that were given up here. Now, what do we mean by a table of integrals? As I mentioned, any calculus textbook is going to have in the back of the book a list of several integrals. Here is one that I pulled from the internet from integral-tables.com, which I've only pulled a few of them off of here, but you'll see that they have ways of evaluating integrals of various forms. For instance, let's look at formula number 32 here. I have 1 over the square root of x squared plus a squared. I'm not really sure how to evaluate that. I'm suspecting, if you're familiar with the technique, that trigonometric substitution would be the way to go with this, and we end up with this formula for that integral. So what we'll be doing in this section is we'll be looking often for some sort of substitution that we can make that will reduce our integral to a form listed in our table of integrals. Again, this table of integrals is limited. There was a second page to this particular table. Most of your textbooks have maybe 5, 6, even more pages of these integrals. Let's take a look at our first example. I see the sine of x dx over cosine of x times the 1 plus 2 cosine of x quantity squared. Now, I take a step back from this and I say, what do I notice about this? What seems like I might want to do here? And I see that I have cosines in a couple of places. The derivative of the cosine is negative sine, and so it may seem that using a substitution, u equals cosine of x, is appropriate. Let's go ahead and do that. Then du would be negative sine of x dx, which means that negative du is sine of x dx. So let's go ahead and make our substitution. Now, we're going to keep in mind that the integral that we obtain may not be something that we're able to evaluate. So sine of x dx is negative du. In the denominator, we have cosine of x, which is u, and then 1 plus 2 times the cosine of x, which is u, quantity squared. Now, some people might know that this would be good to use partial fractions on, but it requires a partial fractions technique that's a little bit more advanced because we have a square factor of a linear function in a linear expression, that 1 plus 2u. So what I do now is I consult my list of tables of integrals. I would show you the one I'm using, but I'm afraid of breaking copyright laws, so I'll just show you the formula that I pull out from my table. In my table, I see I've got du divided by a quantity a times, du divided by u times the quantity a plus bu squared, which seems to fit exactly what I have, except I've got the negative up top. A and B are constants that we have to figure out what they are based on the integral that we're faced with. So in my formula, I have 1 over a times a plus bu minus 1 over a squared times the natural log of the absolute value of a plus bu over u plus a constant c. So I need to match things up. Again, what I'll do is I'll recognize that I have the negative there, but I see I've got 1 plus 2u. They have a plus bu, so in our case, a will be 1, b will be equal to 2. We'll just go ahead and put things in. So we end up with the opposite. Now we've got to be careful. This is multiplied by a difference here. I've got 1 over a. We decided that a was equal to 1, but I'll put that in there. Times a plus bu, 1 plus 2u, b is equal to 2. Minus 1 over a squared, well 1 is 1 squared. Times the natural log of the absolute value of a plus bu, 1 plus 2u, divided by u. That's not a constant. And then we'll put our plus c on the outside. Our final step then, I'm going to make one little substitute or one little simplification by distributing the negative to both terms. But what we do from here is we go back and we resubstitute. We knew that u was equal to the cosine of x, so we'll resubstitute and I'll distribute. So I'll have negative 1 over 1 times anything is just the anything, 1 plus 2 times the cosine of x, minus 1 over 1 squared is just 1. Now I've forgotten that I have a negative on the outside that I'm going to be distributing to the negative on the inside, so this really is plus the natural log of the absolute value of 1 plus 2 times the cosine of x divided by the cosine of x plus a constant. For our second example, let's look at this particular function, x squared dx over the square root of 48 minus 3x squared. Often these tables of integrals will be grouped by the type of integral you're dealing with. Maybe it's integrals involving trigonometric functions or inverse trigonometric functions, exponential functions. One category that you'll often see is one where you have something of the form of the square root of a squared minus u squared. And I kind of see that here, except I have this 3 that's lurking out in the front, and I'm bothered by that 3. So we have to think about how we deal with it. There are actually 2 ways we can deal with it. We could make a substitution for x that would acknowledge the 3's presence, or I noticed that 48 is a factor of 3, so what I'm going to do first actually is I'm going to go ahead and factor the 3 out of there. So I've got x squared dx times this over the square root of 3 times 16 minus x squared. And then I'm going to use a property of square roots. If you take the square root of a product of 2 numbers, it's the product of their square roots. And so we can pull the 1 over the square root of 3 out in front of the integral, and then I have x squared dx divided by the square root of 16 minus x squared. Now I'm bothered by the 1 over radical 3 out front, but the integral that I have to evaluate is simpler than it was before. Now what I do is I consult my table of integrals. There's no substitution really needed this time. I consult my table of integrals to see one that has a form where I have the square of the variable in the numerator over the square root of a squared minus u squared. I've consulted my list of integrals and I find this formula that seems to match what I have. In our particular case, I'm doing the 16 minus x squared under the square root, so it seems to me that 16 should match up with the a squared, which means that a would be 4. We often just take the positive root. It's actually often, or not often, we always just take the positive root for such things. So when we do this, we'll end up with 1 over the square root of 3. Now, once again, our formula involves a sum, and so we want to put parentheses around this. I'll have negative u over 2. Well, our u is x, so negative x over 2. And then it's going to be times the square root of a squared minus u squared. Well, a squared we already said was 16, so it's going to be 16 minus x squared minus, actually plus, excuse me, a squared again is 16 divided by 2 times the inverse sine of a over u. Our a is x divided by our u over a, I'm sorry, the inverse sine of u over a. So that'll be x over 4. And then we'll put our plus c out front. So if you want, you can make a couple little simplifications, maybe distribute the square root of 3 through, and then acknowledge that 16 divided by 2 is equal to 8. So if you want to, you could write it as negative x over 2 radical 3 times the square root of 16 minus x squared plus 8 divided by the square root of 3 times the inverse sine of x over 4 plus a constant. If you were interested in trying to figure out how to do this integral, how to come up with the formula that we have here, you could use a trigonometric substitution in order to do that. Again, once again, the tables are there, so we're going to use them, but it's not a surprise to me that the inverse sign pops up in all this because I have the square root of, it looks kind of like the square root of 1 minus x squared in the denominator, and the derivative of the inverse sign is 1 over the square root of 1 minus x squared. All right, for this next example, we have another instance of a square root. Some of these tables that you'll encounter will have things like the square roots of sums of squares of things, like a squared plus u squared, differences, a squared minus u squared minus a squared. Not too many of them will have things where you have something plus something to the 8th power. And so we might start to think about that x to the 8th that's in there, and we might think, hey, wait a minute, x to the 8th is something squared. And in fact, if you're using properties of exponents, you'll know that that's x to the 4th squared. So it might make sense to let u be equal to x to the 4th. Unfortunately, there would need to be an x cubed, I've written it up there, in the numerator, but it's not there. So this one's kind of a sneaky one. We're gonna play a little bit of a fast and loose with things here. Let me erase that x cubed there. I'm going to actually reintroduce the x cubed. If I introduce an x cubed in the numerator, that would mean I would need to introduce an x cubed in the denominator as well to keep things equal. Well, if I introduce an x cubed in the denominator, that would be x cubed times x to the 5th, which becomes x to the 8th. And then we have the square root of 4 plus x to the 8th dx. Now things are starting to look pretty good for me. I'm going to make two little adjustments here. I'm going to use this fact that x to the 8th is x to the 4th squared. And this is going to become, in the numerator, x cubed dx. In the denominator, we'll have x to the 4th squared times the square root of 4 plus x to the 4th squared. And now the substitution seems to be appropriate. So I'll let u be equal to x to the 4th. Du is 4x cubed dx. I have the x cubed dx. I don't have the 4, so I need to multiply both sides by 1/4. And so I end up with 1/4 du is equal to x cubed dx. When I make my substitution then, I end up with something like this. We'll put the 1/4 out front. Integral x cubed dx is 1/4 du. I've got the 1/4 there. There's my du. X to the 4th was u, so this becomes u squared times the square root of 4 plus u squared also. So now it's time to consult my table of integrals. Here I see something where I've got this form of the square root of something squared plus u squared. This is an a squared plus u squared thing, and so I look and I find this formula. Has the right form. We have 4 plus u squared, so I think that my 4 is going to play the role of that a squared. A squared is going to be 4, which would mean that a is 2, but I don't think we're actually going to need that. according to the formula, we'll get a negative out front. So let's put that in front of the 1/4. There's only one term here, so I don't really need those parentheses. A squared plus u squared, in our case, is going to be 4 plus u squared. And then in the denominator, we've got a squared times u. A squared we said was 4, and then a u, plus a constant. And now I make our substitution, and since I'm running out of room, I'm going to go ahead and substitute and simplify things a little bit. If u is equal to x to the 4th, then u squared, which I have in one place, is going to be x to the 4th squared, which we already said was x to the 8th. So this becomes negative square root 4 plus x to the 8th divided by, I'm going to multiply these two 4's together to give me 16, and then u is x to the 4th plus a constant. All right, for our final one before one that we call a reduction formula, for our final one, I see here that we have cosine of 7x times the sine of 12x. So how do we go about doing this one? Well, we're going to look in a section of our tables of integrals that involves sines and cosines. And I find this formula. It's actually based upon a trigonometric identity. So all those days of your trigonometry teacher saying, hey, pay attention, this is the day that you need that. So in our case, our A is going to be 7, and B is 12. Be very careful that you don't say A is 7x and B is 12x. Now this is kind of a messy little creature here. We're going to do the cosine of A minus B. So in our case, it's the cosine of 7 minus 12, but that whole quantity is multiplied by the x. And that's going to be divided by 2 times 7 minus 12. And then we're going to do minus cosine of, we're going to take the sum of those two values, 7 plus 12 multiplied by x, divided by 2 times the 7 plus 12. And so, simplifying, we have cosine of negative 5x divided by negative 10 minus the cosine of 19x over 38. And then we'll throw on our constant. I didn't put the constant on there before. For our final example, we're going to look at the integral of the tangent to the 6th of x. What we're going to use here is something that's known as a reduction formula. A reduction formula is one where we take some number, in this case it's 6, and replace the integral by another integral where that 6 has been reduced to another power. So let's look for a formula that applies here. And here's the appropriate formula. If you take the integral of the nth power of the tangent, you get the n minus first power of the tangent minus the integral of the n minus second power. So we're going to reduce it by 2. In our case, we're going to use this formula with n equal to 6. When we do this, we'll end up with 1 over 6 minus 1 times the tangent to the 6 minus first power of x, and then we subtract the integral of the tangent to the 6 minus 2 power of x dx. Now I'm throwing in some extra steps here. We'll probably cut things short when we do the next couple of steps here. But we have 1/5 tangent to the 5th of x minus the integral of the 4th power of the tangent of x dx. So we've taken the 6th power and reduced it to the 4th power here. Well, if I look at my formulas again, I do not have one for the integral of the 4th power of the tangent, so I have to use my formula again. This time, however, we'll do it with n equal to 4. Now be careful, you've got this negative out front. Our formula is a difference of two things, and so we need to make sure that we put parentheses in. So I have 1/5 tangent to the 5th of x minus parenthesis. We're going to do 1 over n minus 1, but here n is equal to 4, so we're going to get 1/3 tangent to that same power, the tangent to the third power, minus the integral of the tangent to the n minus 2. N being 4, we'll end up with 4 minus 2, which is 2, tangent squared of x dx. Okay, so now what? Well, now we have to find a formula for the integral of the tangent squared. I will tell you that in my particular table of integrals that I use, there is an explicit formula for that one, but I'm going to show you how it comes about as opposed to just writing it down from there. Oops, and I lost my tangent cubed of x. There we go. I'm going to distribute the negative through here. So minus 1/3 tangent cubed of x plus, okay, so here's how we can do this. I remember this formula, 1 plus tangent squared of x is equal to the secant squared of x. Now, of these three terms, I can find the antiderivative of 1. Ta-da! I don't know what the antiderivative is of tangent squared, and that's what I'm looking for. But I do know a function whose derivative equals the secant squared. So if I solve this for the tangent squared, I get the secant squared of x minus 1, and so my integral becomes the integral of secant squared of x minus 1 dx. Now here's the great thing about that. I don't need to consult the integral tables again. So we get 1/5 tangent to the 5th of x minus 1/3 tangent cubed of x. And now I know what function's derivative is the secant squared. It's the tangent plus the tangent of x. And then I need a function whose derivative is 1, or minus 1, which would be minus x. And then we'll do a plus c. If you step back for a moment, you can kind of see the pattern that's taking place. We have 1/5 tangent to the 5th, minus 1/3 tangent cubed, plus 1/1 tangent to the 1st of x. Where this extra x comes from, well, I know where it comes from. It comes from that minus 1, but that's, in some sense, it doesn't fit the pattern, but it's kind of nice to see the patterns as they go.